Okay, this is the lecture video for MAC1114 Trigonometry. We're in section 8.1 where we're going to take a look at the applications of right triangles. And I'd like to begin that with a review of the formulas concerning right triangles. So in this first box you see the Pythagorean theorem. I'll just abbreviate that, which we have used very often in this course. And that just states, based on the way this right triangle is labeled, hypotenuse squared is equal to leg squared plus leg squared. You can write it like that in its most generic form so that it applies regardless of how the triangle is labeled. But according to the way this is labeled, that would be c squared is equal to a squared plus b squared. Hypotenuse always kept by itself. Each one of these lengths is squared. This is just a statement about the two acute angles inside the right triangle. This is your right angle, and each of these angles are called acute angles because each of them is less than 90, which is why they have to be summed together to equal the other 90 degrees in the triangle. So just to review, some really basic formulas that you've used a lot throughout the course in chapters 6 and 7. Likewise, you have also used these formulas. There is a way to abbreviate all 6 of these formulas, and that is SOHCAHTOA. It's just a way to remember all 6 formulas. Every 3 letters stands for one of these formulas. And actually, you're just going to go using the first 3 letters. That would be the sine formula, which is opposite over hypotenuse. The first letter will always stand for the name of the trig formula, and then this is the ratio that defines the formula. So sine formula is defined as opposite over hypotenuse, which is right there. Cosine is defined as adjacent over hypotenuse, and tangent is defined as opposite over adjacent. These will become very, very important that you know these formulas rather than just knowing them by using various letters that are used to label it. Just knowing these generic formulas, because if you can get sine, cosine, and tangent, you can flip each one of these formulas over to get the other 3 formulas. So for instance, if sine is opposite over hypotenuse, and you know that sine is the reciprocal cousin to cosecant, just do the reciprocal of this formula and you have the formula for cosecant. If you have cosine and you know secant is the reciprocal of cosine, again, flip over this definition, which is contained within this mnemonic device, which is just a way of memorizing all of these formulas. Flip that definition over, you have the secant formula. Likewise for tan and cotan. So these are the formulas that we're going to be using throughout the whole section, because everything in this section will have to do with some type of application problem concerning right triangles. There's a couple of problems that have to do with other theorems that are in the section, but the majority of the problems, you'll have a picture of a right triangle or some word problem leading up to a picture of that nature, and you will be using these formulas up here. Okay, I wanted to mention some things from geometry, just in case you have forgotten them, and that is what is an angle of elevation and what is an angle of depression, because those phrases will be used quite often in some of the word problems that they're going to throw at you in this section. Angle of elevation as well as angle of depression is always measured from the horizontal. So for instance, here's the horizontal line right here, and if you have to look up in order to see something like, let's say, something that's up in the sky, and the angle through which you raise your line of vision, that's called the angle of elevation. So if you have to look up from the horizontal, that means you are elevating your your line of sight, and so that's called the angle of elevation from here to here. However, let's say that you are at a higher elevation yourself. You could look out on the horizontal, but let's say that there is something below where you're standing and you have to lower your line of sight. So when you have to lower your line of sight to see something below you, that's called angle of depression. If we talk about angle of elevation and angle of depression in the same picture with respect to parallel lines, you're going to see that they are actually equal, and that is a theorem from geometry, and I'll point that out to you when we get to problems concerning angle of elevation and angle of depression. Okay, another theorem that is in this section that we have not used, I don't think, in any of the other sections, and these are the complementary angles. So, the complementary angle theorem, you have to know what two trig functions are complementary partners. You have to memorize these pairs so that you can apply the complementary angle theorem. So, the pairs with respect to a complementary relationship are sine and cosine, tan and cotan, secant and cosecant. And what this theorem states is that once you pick out two angles that are complementary angle partners, like sine and cosine, whatever angle you use here, that should be the angle, the complementary angle is what you should be using for this other angle. And just as a little proof that complementary angles follow this theorem, so we have sine of 30, and that's equal to some value. But as long as we are plugging in our calculator cosine of 60 degrees, 60 is the complement of this. If this was a 20, this would be a 70. Remember, a complementary pair are two angles, two acute angles that add up to 90. Just like in a right triangle, the two acute angles always add up to 90. So, being that sine and cosine are complementary angle partners, you can rewrite anything as long as the angles that you're using here for sine and cosine, as long as they are complements. And you can even show yourself this in the calculator. Let me make sure my calculator is in degrees. It is. So notice that if I press in sine of 30, I get this answer. And if this is true, this particular theorem, then cosine of 60 should also give me the same answer. So just as a little proof, let me demonstrate that. And notice that you get the same thing. Now this would apply for anything as long as you are using two trig functions that are complementary partners. You can't take sine and pair it up with any other, with whatever trig function you want. If you're going to try and apply this complementary angle theorem, that you have to memorize the pairs that are considered complementary trig functions. So let's say I did sine of 20 degrees, use its complementary partner, which is cosine, and make sure you use the angle that is complementary to whatever you've chosen to use here. Once again, if you put that in the calculator, you will see that they are the same value. Sine of 20, there's sine of 20. And then cosine of 70 should be equal to it. And you see the same value. So all this is stating is you have to know the two angles that are complementary partners and make sure to use complementary angles here, and you will get the same value either way. This theorem is going to help us to rewrite some of the problems that we're trying to simplify but have been asked to do so without a calculator. So it'll come in handy for some of those problems. Okay, so just the first page is just a reminder of formulas and theorems that we have used throughout the book, and then the new complementary angle theorem. Okay, so we have the problems now beginning in example 1. We've just come through the previous chapter where much of what we were studying, the first two sections, in fact, of the previous chapter, and then we had to use it throughout the entire rest of the chapter once we concentrated on inverse trig functions, because the inverse trig function is what gets us the angle. So we went through a whole chapter where we kind of concentrated on that, and so that's how this section begins, because you will be using it quite a bit in the once you get started with the application problem. So just a real quick reminder of what gets you an angle, and that is knowing how to rewrite this as an inverse. Okay, so we're going to do inverse of this value. All that happens is that you switch these two things. The value that you're seeing here comes right up against the inverse, and the theta takes its place. Okay, so we are looking for inverse tangent of 2/5. We want to know the angle that's equivalent to that, and you have to just remember from section 7.1 and 7.2, previous chapter, we learned that when we're dealing with inverses, those inverses have restrictions. The restrictions for inverse tan are the following, because otherwise you're going to be giving two different answers as though you were just being asked to solve the equation in general. Okay, that's where your inverse tangent lies. So the value that you give should be somewhere between here and here. So we're going to look at two different things. We want our tan value to be positive, because look at the original nature of the equation. In its original form, you can see tan is a positive value. So we want tan to be positive, yet if you were to move down into this quadrant, you only have a choice of either being here or here. We are going to get our calculator to help us. But sometimes if we don't have some sense of what's going on and the restrictions that are involved with inverse values, we pick the wrong quadrant. So we have to have a working knowledge of that. Okay, notice that in this quadrant down here, x's are positive, but y's are negative, which would make your tan value, which is made out of y and x, it would make it negative. Therefore, you have to be in this quadrant. So you're going to make sure that whatever your calculator does offer you, that it's in quadrant 1, not in quadrant 4. Okay, so let's see. We're going to get an answer in degrees. That's what's been asked for here, round to 1 decimal place. So we're going to go second, inverse tan, and we're going to put in there 2 divided by 5. Okay, and then we get 21 rounded to 1 decimal place would be 21.8. Okay, so just a reminder of how to get the values using the inverse function. Okay, and problem number 2. Problem number 2, it says if theta is an acute angle, solve the equation cosine of theta is equal to square root of 2 over 2. Again, you can get your calculator to help you, but first, have a working sense of what quadrant do you need to be in with your answer. Now this, you can see cosine is positive, so we want to be in a quadrant where the cosine, which is really just x over r, if you remember the definition for cosine, we want to be in a quadrant where cosine is positive, which means you need to be in a quadrant where x's are positive. You want to get your calculator to help you out with the angle portion of this. You are trying to find theta, and you can only do that through inverses. Now, some of these values you're just going to know right off the top of your head just because you've worked with it so much. But like, for instance, when you're looking at this original equation here, a lot of students, once you get to chapter 8, because we've worked with these particular values in a special right triangle, because we've worked with it so much, you probably already know what your calculator is going to tell you. This is the 45-degree angle. Cosine and sine are both square root of 2 over 2. Remember that 45, 45, 90 triangle where both legs are square root of 2 over 2? Well, that's your classic special right triangle that has 45-degree angles as both of the acute angles. Again, however, you can get your calculator to help you out with that if you don't remember that. Okay, you can just put it right in there like that. Let's have a sense of where are we restricted to when performing inverse cosine. So the restrictions from the last chapter are from here to here whenever you're doing inverse cosine. Okay, we can't possibly be over here because we want cosine to be positive, therefore we must be in this quadrant right here. So just keep that in mind when using your calculator. Okay, so this is going to be second inverse cosine, and we're going to put in second square root of 2 divided by 2. Close that up. And you see we get 45 degrees. So theta is equal to 45 degrees. Okay, so just a little reminder of how to get your calculator to help out when looking for angles. Okay, moving to this next picture. In examples 3 and 4, we're going to find the value for each of the 6 trig functions. Give exact answers only, so you're going to demonstrate your knowledge of how to deal with fractions as well as radicals. So what it means by giving an exact answer. Do not go to your calculator to get a decimal form of the answer, because that's going to make you skip over all the fractional and radical knowledge that you're supposed to be demonstrating. Okay, so let's get at it. When it says to find sine of theta, that means you should be standing on theta when doing sine, cosine, cosecant, all of these. You should be standing in a specific location, and that'll be the angle that they mention right here. Because when you start doing opposite over adjacent and opposite over hypotenuse, that's all about where you're standing. What is the side that is opposite to you is dependent on where you're standing in the triangle. So you can't just use those definitions, x over r, y over r, because that's all dependent on where you're standing. So make sure that you are standing on the angle that is mentioned. Okay, so if I'm standing right here and I'm trying to do sine, remember sine is defined as, you can use your SOHCAHTOA if you'd like to remember the formulas. Okay, so here's the sine formula, which is just opposite over hypotenuse. So if I'm standing right here, I'm going to need this piece right here, and then my hypotenuse. The hypotenuse doesn't change no matter where you're standing, but opposite and adjacent do. So I noticed that I need opposite here, but yet I don't have that. So you're going to have to go to that Pythagorean theorem that was introduced in this section, find the missing piece, and then you can go about your business of finding anytime you have a triangle that's missing a side, typically they're going to ask you for an answer that involves one of the missing pieces, so we might as well find that now. Okay, so starting off with Pythagorean, and then we'll come back to using this SOHCAHTOA. Okay, so it's hypotenuse squared is equal to leg squared plus the other leg squared, and I'll just call this x. Okay, so this is going to be 18 squared, which is 324. And then the 9 squared is 81, and then we have x squared. Then we're going to bring this 81 to the other side. That'll give us x squared is equal to 243. Okay. 1 second. Okay, then we are going to solve for x by getting rid of the square, taking the square root to do so. And see, and this is where you're going to be demonstrating that you have mastered the kind of simplifying steps from the previous courses. So there is no exact square root for 243, but there's a partial square root. So you want to try and break down this 243 into something, into a product of two factors, and one of them should be something that there's a square root of. So if this ends in 3, it's divisible by 3. So I just tried dividing 3 into this, and it turned out to be 81 times 3, which is perfect, because I can take the square root of this, which comes out as a 9, so we're done dealing with that, and then the 3 stays inside. Okay, so that's called using an exact value, not a decimal approximation, which would allow you to skip over all these steps, and you're expected to be able to show them. So this is going to be 9 square roots of 3. So now we have the missing piece, and we can find all 6 trig values using SOHCAHTOA. Okay, so this is opposite. If I'm standing right here, this would be opposite 9 square roots of 3 over hypotenuse, which is 18. Okay, and then you're going to reduce that. This ends up being, 9 goes into itself once, and it goes in here twice. So this would end up being square root of 3 over 2. Squeeze that in right there. Okay, cosecant is going to be the reciprocal of this. This is the reciprocal partner to this. So this would be 2 over square root of 3. Just the reciprocal, and then you're going to be expected to understand the skills, have the skills for rationalizing these answers. So this was your answer for sine, and I'm going to simplify this further by going square root of 3 over square root of 3, and that'll give me 2 square roots of 3 over 3. And that will be my cosecant answer. As far as cosine goes, cosine is going to be, according to SOHCAHTOA, cosine is adjacent over hypotenuse. So get right back in that position that you're supposed to be on, which is theta. You're always standing on the angle that comes right after the trig word. So adjacent is the leg that runs right into the angle that you're standing on. So that's going to be 9. And then the hypotenuse is 18. Go ahead and reduce that. Okay, so that'll be my answer for cosine. And then secant is the reciprocal partner to this. So this will just end up being 2. And then for tan, here's the formula down here, TOA. Tan is opposite over adjacent. Okay, so if you're standing here, opposite would be 9 square roots of 3, and adjacent would be the 9. So this would simplify, the tan value would simplify into square root of 3. The reciprocal of that, which would be cotangent, would be 1 over square root of 3. Instead of square root of 3 over 1, 1 over square root of 3. But you need to rationalize these answers, so you'll have to multiply the bottom as well as the top by square root of 3. And that'll give you square root of 3 over 3. Okay, and that completes all 6 answers. Okay, moving to example 4. Example 4, same thing. Working with radicals. This time your theta is down here. Remember, you need to be standing on the angle that is mentioned here as you call out opposite and adjacent. So once again, we'll use SOHCAHTOA and we will use Pythagorean theorem. You see once again that there is a missing side. Let's go ahead and get that because it's going to be required in some of these answers. So it's hypotenuse squared. This is the hypotenuse. It's always hypotenuse squared. I'll just write that up here. Is equal to leg squared plus other leg squared. Okay, we do not know this leg down here. I'll call it x. We do know one of the legs. We don't know the other one. Okay, so this is going to be 29 because when you square a square root, it just makes the square root come off. Over here we have 5. Over here we have x squared. So if we were to bring this over here, in other words, subtract 4, we would end up with 25 equal to x squared. And therefore x, after taking the square root of both sides, x would be equal to 5. Let's write that a little bit nicer. Okay, so we have 5 more. Okay, so now doing sine, cosine, tangent, and then all the reciprocal cousins. We can just use SOHCAHTOA to remind us of all the formulas. So sine is opposite over hypotenuse. Okay, standing right here, opposite would have to be the 2. Opposite means the side across from you. And then hypotenuse, no matter where you're standing, is this slanted side across from the right angle. So that would be square root of 29. Okay, but you cannot give that answer because you have a radical in the bottom. So you are going to simplify this. I'll do it down here. Move it out just a little bit. Okay, so I'm going to simplify this. I have 2 over square root of 29, and I'm going to get rid of that radical. In other words, do what we call rationalizing. By multiplying bottom and top by square root of 29, and that'll end up with 2 square roots of 29 over 29. So I have my answer for sine of theta. Okay, then when you go to get cosecant, it's going to be the reciprocal of this. However, you know, I would look backwards a little bit. We got this answer. Right before that, we were at this stage. Right before that, we were at this stage. When we originally did sine before it was simplified, it was 2 over square root of 29. I think that's what I'm going to flip over, because if I flip this over, I'm going to be right back to having a radical in the denominator. So flipping this over, I would end up with square root of 29 over 2, which is the reciprocal of what I had for sine. This is just it in its simplified form or rationalized form. Okay, cosine. Cosine is going to be adjacent over hypotenuse. How much room here? And adjacent is going to be this leg right here, the leg that runs into the angle that you're standing on. So that's going to be 5 over the hypotenuse, which is square root of 29. Okay, that is the answer in unrationalized form. So by the time you rationalize it, it is 5 square roots of 29 over regular 29. Okay, and that is what your cosine is equal to. Okay, if you're going to give the answer for secant, it would just be any version of this flipped over. So I'm going to flip this over. Cosine flipped over would be square root of 29 over 5. So that reciprocal is what your secant value is equal to. Okay. All right, let's move on to tan and cotan. So tan is opposite over adjacent. So opposite over adjacent. And then my opposite from where I'm standing would be 2. And then my adjacent would be 5. Okay, and then when you go to do cotangent, it's just the reciprocal of this. So instead of 2 over 5, 5 over 2. Okay, so basically the same thing that we did in example 3. Just wanted to give you some practice using Pythagorean theorem to complete the triangle. In other words, find any leg or hypotenuse, any side that happens to be missing. And then using SOHCAHTOA, which actually has all 6 formulas in it. And you can just get the reciprocals the minute that you get sine, cosine, and tangent. I mean, if you want to be looking at this for the formulas, you can just take any one of these, sine, cosine, or tangent, and use it backwards. So reciprocal, if sine is opposite over hypotenuse, just use this formula in the opposite order, hypotenuse over opposite, and that would be cosecant. But I prefer to just get sine, cosine, and tangent, and then right away get their reciprocals instead of looking at this for each one. Okay, so that's all 6 there. Then we come to examples 5 and 6, and both of these have to do with the theorems that we looked at on the first page called the complementary angle theorems. You do not have the ability to know what the value for sine of 67 is, nor do you have the ability to know what the cosine of 23 is unless you use your calculator. Yet this is telling you do not use a calculator. Therefore, you need to know how to get to the exact form of the answer without introducing decimals. So what you can do to get around that is to use the complementary angle theorem. For instance, and there's 2 different ways you could go about this problem. You could either rewrite this term using the complementary angle theorem, or you can rewrite this term. So it really doesn't matter which way you go. I'm going to rewrite this guy right here. So it's sine of 67. I'm not doing anything to that term. However, through the complementary angle theorem, all you have to know is which trig function is considered the complementary partner of cosine. It is sine. And when you're using the complementary partner, you must use the complementary angle. The complement of 23 is 67 degrees. Bring down that minus sign. And in this way, you can get the exact answer without introducing decimals. So anything minus itself is 0. And that is the answer for this problem. Likewise, you can get the answer for this without using a calculator by understanding the complementary angle theorem. Again, you can go 2 different ways here. You can either replace cosine of 69 or you can replace sine of 21, either one. I'm going to replace the bottom. So it's cosine of 69 degrees. And then on the bottom, instead of using sine, I'm going to use its complementary partner, which is cosine. And if I'm going to use the trig function that is complementary to sine, I also have to use the angle that's complementary to what you're seeing here, which is 69 degrees. And in doing so, you have a quantity divided by itself, which is always 1. And so you have example 6. Moving on to 7. We haven't really gotten into the application problems yet, the word problems. We're still just seeing if we know the basic mechanics of working with a right triangle. Here where they're just giving you a picture, asking you to use the right triangle and find all the missing values. We're going to round anything to the nearest hundredths if it comes out to be a decimal. So let's see, I'm going to go ahead and put the values that they've given. They said C is 6. They said B is 70 degrees. And you're finding anything that's missing. Now, A is probably the easiest thing to find because these two just add up to 90. These are two acute angles that make up the other 90 degrees in the triangle because 90's already been used there. So A would have to be just 90 minus the 70 that you see right there. These two acute angles always add up to 90 in a right triangle anyway. So 20 for that. Okay, so we have one answer. Okay, then we're going to find A and B. Notice that I cannot use the Pythagorean theorem because the Pythagorean theorem is for when you know at least two sides and you're only missing one. When you don't have at least two sides, then you need to get into the SOHCAHTOA because that will allow you to find a second side based on only knowing one side at the present moment. So it is stronger. Not that it's stronger, but it allows you to find missing sides on a right triangle without knowing so much information. So right now, look at what you have. You have the hypotenuse. So you're going to want to use one of these formulas that has h in it, hypotenuse, so that you can use the one side that you do have. Doesn't matter what side you go after first. You could go after B or you can go after A. Okay, but you do have to be able to stand on a particular angle. It doesn't matter whether you stand on the 70 or the 20. Just make a decision, and you have to be able to call out the names of these sides. Like, is it considered opposite? Is it considered adjacent? So that you can pick out which of these three trig formulas to use. Okay, so let me demonstrate. I have chosen to stand on the 70-degree angle. Not sure which trig function I'm going to use right now, so I'll wait to name it. But I know I want to use hypotenuse, so something with hypotenuse, either sine or cosine. And then I think I am going to go after this side first. If I am going after this side called A, it is called adjacent. The leg that runs into the angle that you're standing on is called adjacent. The other leg is called opposite. So if I have made a choice, and you're making choices here, do you want to stand on 70 or do you want to stand up in the air on the 20? That's a choice that you got to make just before you start your problem. Then you have to decide which one of these are you going to go after first. Are you going after this or that? It does not matter, but it is a choice that you make. So I decided to stand on 70 and to get the A. This is called adjacent. And of course I want to use hypotenuse because it's the only side I actually have a number for. So now, knowing that you're going to be using adjacent over hypotenuse, which one of these is this? It is cosine. Therefore, you have chosen to use the cosine formula. Okay, writing this a little bit more neatly without words, I'm going to go cosine of 70 is equal to adjacent in this picture was called A, and the hypotenuse was 6. So substituting the variables and numbers that are on that specific right triangle, I go from this to this. Now I'm going to go into my calculator, which is why this problem says to round to the nearest hundredth, because they know they're giving you angles that are not from a special right triangle, and therefore you're going to get decimals. So make sure that your mode is in degrees, and mine is, I've already checked it. So cosine of 70, I would carry that out to at least 4 decimal places while you're in the middle of the problem, or else you're going to be rounding too severely. Don't round off to the hundredths place until the end of the problem. Okay, so 0.3420. I'll just continue it right here. Cosine of 70 is point, even though I'm holding the entire exact value in the window still, then over here you have a over 6. And look, you just come up with a little proportion that you're just going to cross multiply your way to the final solution. Now we're going to cross multiply like that, leave the a on the left hand side, still have the exact value here. And rounding off to the hundredths place, that would be 2.05. So there's the A. And then all we have left to find now is B. Once again, you have choices. Now that you do happen to know two of the sides, you could go back into Pythagorean theorem if that's what you're into, or you can continue with SOHCAHTOA. It's up to you. Okay, I'm going to stick with the SOHCAHTOA since that's what we're trying to reinforce here. But again, you're welcome to use Pythagorean theorem. So if I was to stand right here all over again, and again, it's your option. You can stand up here in the air if you want to. You'll still get the same answers if you do it properly. So if I'm standing here and I want B, side B, to be in the problem, where B is, that's considered opposite over hypotenuse. You could get it by going opposite over adjacent. That would be tangent. If you go opposite over hypotenuse, it'll be sine. So that's why you got to wait to see what is it that you're going to be using and what are the names of those pieces. I am going to be using opposite because I want to get B into my problem over hypotenuse. It's just the choice that I have made. Okay, if you're using opposite over hypotenuse, that is the sine function. Okay, getting more specific here, sine of 70, opposite was called B in the picture, and the hypotenuse, we already knew that it was 6. Go to your calculator and get the sine value. Okay, so this is going to be sine of 70, and that'll be 0.9397. Which is equal to B over 6, and then just cross multiply. And if you're rounding to the hundredths place, it would be 5.64. Okay, so those are the two answers for number 7. Number 8, same kind of deal. Practice standing on a specific acute angle and making decisions as to which trig function you're going to use, because you will always have options. So right now I know that A is 1 and I know that C is 4. So now this one you actually could start with Pythagorean theorem because you have enough sides to go and find B right now. So if you did want to start with Pythagorean theorem, that's up to you. Not that you have to, because there's other ways to find it as well. If you did, it would be B squared plus A squared is equal to C squared. Don't forget, whether you put the hypotenuse on the right side or the left side, it must be by itself when you begin the Pythagorean theorem. Okay, so let's go put in the values we have. We have B is just unknown, so just B squared. Whereas the A value is 1 and the hypotenuse is 4. Remember, in this theorem, everything is squared. Okay, so then it's going to be B squared plus 1 is equal to 16. Bring this 1 over to the other side, at which point it will be negative 1, so just B squared is equal to 15. And then finally, B would be square root of 15. Okay, you're giving exact answers. Okay, now we have to find the angles that are associated with these values. So it's up to you which one you want to find first, which one you want to find second. But I am going to, let's see, I'm going to find B first, I guess. And then I think I'll just subtract to find A. So first I'm going to find B. I'm going to stand right on B, and that really matters that you know where you're standing. Because when you start calling out what this is and what this is, it's all with respect to where you're standing. This would be opposite. This would be adjacent. Okay, so one way to find angle B, and I think I will choose that particular method, is to use tangent. Tangent of any angle is equal to opposite over adjacent. You can see that right in your Sockatella right here. Tangent is opposite over adjacent. So getting more specific there, tangent of angle B would be square root of 15. That would be the opposite value, and the adjacent would be 1. Okay. Hold on for 1 second. Okay. So now what we're going to do here is, and I forgot to round this off to the nearest hundredth. So let me go ahead and give that answer, just since the instructions for numbers 7 and 8 was just rounded to the nearest hundredth, so I might as well do that. So B was square root of 15. So second square root 15, and that is rounded to the nearest hundredth would be 3.87. So you can actually use that if you want to, or you can just leave it up like this. So B is approximately 3.87. And then if we're going to do this one right here, you can leave it like this if you want to. It's not going to matter whether you put this in or whether you put this in. Remember that when you want to find an angle, you need to go into inverses. Okay, to go from a non-inverse statement to an inverse statement, you just switch these two. You bring this value right up against your inverse. Square root of 15 over 1 is just square root of 15. And then the angle jumps over and takes its place. And now pop that in your calculator. So it's second inverse. I chose to keep it as a square root. There we go. 75, we're rounding to the nearest hundredth place, so 75.52. And sometimes they'll tell you to round to the 10th place. Sometimes they'll ask you to round to the 100th place. I mean, that's all pretty irrelevant with respect to what you're really trying to concentrate on is all the options you have when working in a right triangle. Should I use Sockatella? When do I have to use Sockatella? When am I forced into doing that as opposed to using Pythagorean theorem? So those are the kind of decisions that is really the emphasis of this section. Okay, so we have angle B as well. And then if you want to get angle A, you could just go like this. These two add up to be 90. So 90 minus the one that you already know, which is angle B, will give you the one angle that you're missing thus far. So 90 minus the answer that's already in the calculator is 14.4. And again, if they want you to round differently, then they'll say so. Sometimes they have you round the angles to the 10th place and the sides to the 100th place. Other problems, they'll just let you round everything to the same place. So, like I said, that's neither here nor there. Okay, here we go for example 9. So this one has a building that is 360 feet tall, casts a shadow 60 feet long. What is the angle of elevation of the sun? So this one I drew out already just to save time. Here's a picture of what they just described. A building is 360 feet tall. In order for a shadow to be cast, the sun would have to be slightly above and behind the building, and then the shadow would be out in front of the building, just like when you're walking on the sidewalk and you see your big long shadow sometimes out in front of you. And so that's the situation here. Okay, the sun is up above the building, casts a shadow out in front of the building, and that shadow is 60 feet. So we're emulating a right triangle here. It also talks about what is the angle of elevation. So let's talk about that. If you are measuring from the sun out to the horizontal, if you were up at that location, that would be called the angle of depression, because you'd have to look down to see this angle right here. So this is called angle of depression. But angle of depression and angle of elevation are equal, and this is why. If you recall from geometry, we have two parallel lines here. The horizontal that's up here and the horizontal that's down here, the floor. This is what we call a transversal. It cuts through both of the parallel lines, the horizontal that's here and the horizontal that's here. So there's a theorem regarding parallel lines, and that is alternate interior angles. In other words, both of these angles are on the interior of the parallel lines, and they're on alternate sides. This angle is above the transversal. This angle is below it. So these are called alternate interior angles, and those kind of angles are always equal. Alternate interior angles, when you're talking about parallel lines are congruent, equal in measure. Okay, so whatever that is what that is. So if, let's see, it says, what is the angle of elevation of the sun? So that's, you just have to know that angle of depression and angle of elevation are the same, so you can drag information that has to do with the physical object inside your right triangle. So this would be a right triangle right here. Okay, we got a 60 there, we got a 360 there, and we're going to try and find the angle. So we're going to get right into SOHCAHTOA, just as we have been for all these problems. I'm going to stand on this angle because I'm looking for it, and I would like to use the sides that have numbers on it. So I want to use opposite, which has a 360 on it, and I want to use adjacent. So I'm standing right here. What is the name of the trig function that uses opposite and adjacent? That would be tangent. So you're figuring out which trig function to use given the pieces that you want in your problem so that you can solve for what they've asked for, which is this alpha. Okay, so it's tan of some unknown angle is equal to 360 over 60. Okay, so 36 divided by 6 is going to be 6. Now we're going to go to our calculator in order to figure out what the actual angle is. Give me 1 second. Okay, so continuing with this problem. Okay, doing what we've done in all the previous problems when looking for an angle. We're going to do inverse of 6 is equal to the angle. Just switch these two when you go into inverse form and then go into your calculator. So it's going to be second inverse tan. Dump the 6 in there, close it, and you have 80 point, let's see what that said to round to the nearest tenth. Okay, so 80.5. Alpha angle is equal to 80.5, and that's in degrees. Okay, so moving on to example 10. Moving to example 10, we have a state trooper. Let's read this carefully. State trooper is hidden 30 feet from the highway. This is the highway. 1 second after a truck passes, 1 second after a truck passes, the angle theta between the highway, this is the highway, and the line of observation from the patrol car. This is the line of observation right here. So the angle 1 second after the patrol car to the truck is measured. Okay, so they're saying it's measured 1 second after it passes. And see the illustration. Okay, so if the angle measures 15 degrees, so they're saying if this is, I don't know if I can fit it right in there, but I'll try. If this is 15 degrees, how fast is the truck traveling? Express the answer in feet per second. So we want to know how many feet is it traveling in 1 second. Express the answer in feet per second and also in miles per hour. Let's just go for feet per second right now. So you're in this triangle. You want to be standing on the only angle that you know so that you can classify these sides as opposite, adjacent. With respect to where I'm standing on this 15-degree angle, this would be opposite. This is adjacent, so I am using tangent. So it's tangent of 15 is equal to opposite over adjacent. That's from Sokotoa. Opposite would be 30 feet, and adjacent would be x feet. Okay, we're looking for how many feet per second. We already know this is 1 second. How many feet does it travel in that second? So I just called it x. So we're going to get this from the calculator. So tan of 15. I'll just write 0.2679, but I'll have the whole thing still there in the calculator window. Is equal to opposite over adjacent. Okay, so cross multiplying is going to get you out of this too. I will mention a shortcut here. Yes, you could cross multiply this x right up alongside the 0.2679, but then you'd have to divide by 0.2679, thus going through 2 steps. Okay, you could do it that way. Cross multiply this x right up here. It would be x times 0.2679, and then you'd have to divide both sides. Or you can do it in just 1 step. When the variable you're solving for is in the denominator, this is a shortened version of one-way cross multiplication. Just switch these two. Because you're not truly getting the answer unless the value that you're looking for is in the numerator. So this comes up here where the 2679 is, and the 0.2679 takes its place. So just swap places there. Now pop it in your calculator. Okay, so this is going to be, put up here where you can see it, 30 divided by this answer that's still in the window. So I'm going to press second answer, and I'm going to get 111.96. We'll take it to the hundredths place. Let's just take it to the hundredths place here. Okay, so I'm going to go 111.96. Let's go grab those units. So this is in feet, because that X stood for feet. Feet per second. Okay, this picture is regard with what distance was traveled in 1 second, and that's what I solved for. So I've gotten the answer in feet per second as requested, and then now I'm going to get it in miles per hour. Okay, so now let's take this, bring it right up here, 111.96 feet per second, and I'm just going to I'm going to work with the units until I get them converted to miles per hour. So first thing I'm going to go after is getting rid of feet and taking it to miles. So this is called dimensional analysis. It's used in many math and science courses. Okay, I want feet to go away, and I want to get into miles. If you want a unit to go away, that unit has to appear in both the numerator and denominator in order for them to cancel. The numbers that I'm going to put here are the equivalencies between miles and feet. There are 5,280 feet in 1 mile. Okay, I'm not going to calculate yet because I'm not going to put it in my calculator yet because not only do I want to get rid of feet, I also want to get rid of seconds. They said that they want the answer in miles. I've already gotten that to happen. There's miles in my answer. I want the unit of time to be hours. So now I'm going to get rid of seconds. If seconds are at the top, at the bottom, then I'll put mine at the top. 60 seconds, I can go to minutes. There's 60 seconds in 1 minute. Okay, that would get rid of seconds and have me in minutes, but once again, I want to be in hours. So let's go one more time. There are 60 minutes. This will get rid of minutes because I have minutes in the top, minutes in the bottom, and take me into hours. These are equivalent, just like these are equivalent, just like these are equivalent. You should know how to use dimensional analysis when you get to this level. So we will practice it here and whenever we get a chance. Okay, it's just for converting units. So let's see. What here cancels, if anything? Okay. So we can just pop all of this in our calculator. Now anything that's in the numerator, you multiply those, you do a product, and anything that's in the denominator is a divisor. So let's get all of our tops multiplied together. So it's 111.96, which I still have in my calculator window, times 60 times 60. Okay, so there's the top. And then the only divisor that I have that's not a 1 is the 5280. So divided by 5280, and that gives you 76.3. And we're going to round to the hundredths place, so 76.34. $76.34, and the units that are left here, let's cancel out anything that's gone. Minutes are gone, and all we have left is miles up at the top, hours down at the bottom. So the units there would be miles per hour. $76.34 miles per hour. Okay, so then let's see what else have they asked us to find here. The other thing that we're being asked to find in part B, let me write this a little bit clearer just in case you can't see that, 76.34 miles per hour. Okay, in part B, it says if the speed limit is 50 miles per hour and a speeding ticket is issued for speeds of 10 miles per hour or more, so they start at 60 miles per hour, the speeding tickets. For what angles should the trooper issue a ticket? For what angles should the trooper issue a ticket? Okay, so let's see. Why don't we start off with the fact that now we're going to find the angle associated with it. We want to know, since this is in feet, we want to have something here that's in feet. So I think what I'm going to do is we're going to work backwards here. We're going to go 60 miles per hour is where those tickets begin. And if I'm going to bring this all the way back to feet, again, I want to have a distance that's in feet, because if one side is in feet, you want the other side of the triangle to be in feet as well. So I'm going to get rid of the miles. In 1 mile, there is 5,280 feet. And since we're talking about a unit of time in this picture that's in seconds, I also don't want this hour, this unit of hours. I want seconds. So this will get rid of miles. And now let's work on getting rid of hours. In 1 hour, there is 60 minutes. But let's take it to seconds. So hours are gone now. We're in minutes as a unit of time. And then in 1 minute, there's 60 seconds. Okay, so minutes would be gone. So the only units that we would have left, which are compatible with this diagram, is feet, right there, and seconds. Okay, we got seconds as our unit of time, feet, and that's how you want this information to be, knowing that this is the information that goes with the moment at which tickets are issued, which is for 10 miles per hour or more. So they start here. Okay, so let's see. Now we can go, let's see what cancels here. This 60 would cancel, just so I can avoid putting in more numbers than I need to. All I really need to put in my calculator, and I'll do it down here, is 5280 divided by 60, because everything else is a 1. 5280 divided by 60 would be 88 feet per second. Okay, so what is that saying? That in 1 second, this distance would be 88 feet, and that is the point at which tickets start getting issued. So the question was, for what angles should the trooper issue a ticket? Okay, so let's see. Now the second part of the problem is to find the angle. So because I have opposite and adjacent, I could get into tan. Tan of the angle that I'm looking for is opposite over adjacent. And so it's tan of theta 30 divided by 88 is approximately 0.3409. I want to find the theta that's associated with this, so I get into inverses, which is pretty much what the whole section has been about thus far, reminding you how to get angles so that you could solve these application problems. So the value comes up against the inverse trig function, and that's how we're going to find this angle. So whole thing is still there in the window. Let's go second inverse, dump in that decimal, and we get 18.8 . I'm just going to leave it at the 10th place as degrees, 18.8 degrees. And let me check. I want to check the answer before I move on. Yep. Okay, so yes, that is at 18.8 degrees. So if the angle is equal or less than 18.8 degrees, a ticket should be issued. Okay. All right, moving on to number 11. Okay, so let's see, what's this next one? The next one is a security camera in a neighborhood bank is mounted on a wall that's 11 feet above the floor. What angle of depression should be used if the camera is to be directed 6 feet above the floor, but 15 feet away from the wall? This one I also drew a picture for. See if you can understand what's going on here with respect to these words. Okay, you have a camera on the wall. Here is the wall. I've drawn a camera here that can rotate down. It can stay like this. It can stay straight out, but it can rotate. It's right on a hinge right here. It's located 11 feet up the wall. So this is the floor, and it's 11 feet up in the air. What angle of depression, that would be that right there. What angle of depression, you can name this angle any kind of symbol you want, should be used if the camera is to be directed to a spot, here's the spot, that is 6 feet above the floor. This is your floor. Okay, that spot is 6 feet above the floor, but 15 feet away from the wall. Okay, so this represents the wall that the camera is positioned on. Okay, so you have a wall, camera's 11 feet up, then there's a spot that the camera is looking at, and it is 6 feet up from the ground floor and 15 feet away from the wall. So this represents everything that is being discussed in this word problem. And they want to know what angle of depression should be used. That second sentence right there. What angle of depression should be used? So we're solving for alpha. If you're trying to drag something that's on the outside of the triangle to the inside of the triangle, then you have to remember, you got a horizontal line here, and the floor represents a horizontal line. This hypotenuse would serve as the transversal, that if I made it longer, it would cross both of the parallel lines. This angle and this angle right here would be called alternate interior angles. They're on alternate sides of this transversal, but they're on the interior of the parallel line. So those are considered equal. Okay, so even though they talked about angle of depression, we can drag that right into the triangle. So we're inside of a triangle. Okay, let's try and also get either this piece or this piece. I think from the information that we have here with respect to the spot, it is 6 feet up in the air. This whole wall is 11. So if you just want to know what this is, all you have to do is go 11. Take this entire 11 and take this piece off right here. Subtract 6 and you will get 5 feet. Okay, with all that junk in the way, I moved the picture over here as well. You have 5 feet for one side of your triangle. We're concentrating on this triangle. All that other information was just so that we could label as much of the right triangle as possible. So now we have a 5 foot there, we have a 15 foot here. We have an angle that we're looking at, and we can use tangent. Because if we're standing on alpha, and we want to drag these two numbers into it, we could use opposite over adjacent. That is how tan is defined, opposite over adjacent. So we would have tan of some angle is 1/3. If we want to know what the angle is, we get into inverses. So it's second, inverse tan, 1 divided by 3. Close that up, and we have 18.43. Going to round this to the 10th place. You'll round to whatever they ask you for in the problem. Okay, that's the angle that should be used. Okay, moving to, so this was number 11. You can fill that in on your outline. Okay, moving to the next problem. Number 12. Okay, problem number 12. It says, a DC aircraft leaves an airport from a runway whose bearing is north, 29 degrees east. After flying 1/4 of a mile, the pilot requests permission to turn 90 degrees and head towards the southeast. Let's stop right there. I'm going to give you a diagram where I have begun to draw these situations that are spoken about in this problem. Okay, just so you can look at the words and what I'm drawing here. Okay, so if you're going to do anything that has to do with north, south, east, and west, you need a directional. You got to start off with having a pole that shows the north direction and the south direction. This would be west, this would be east. They don't talk about anything west, but if it comes up, we can always just extend it out that way. Okay, so north and south, west and east. Okay, so let's read these words again. An aircraft leaves an airport. Here's my airport. It's like the origin. Leaves an airport from a runway whose bearing, that's the bearing of the airplane, is northeast 29 degrees. That means it is 29 degrees rotated from north to east. So starting from north, rotate 29 degrees as you're heading towards the east direction. So rotate towards the east, but 29 degrees, and that is the path that this plane is on. So it's traveling along this north 29 degrees east bearing, right on this path right here, and then all of a sudden it requests permission to take a sharp right of 90 degrees. And this is after it flies along this path for a quarter of a mile, and that is what I've labeled right here. Okay, once again, it left the airport on a northeast bearing of 29 degrees. That means 29 degrees away from the northern direction, but towards the eastern direction. It travels a length or distance of a quarter of a mile, which is the same thing as 0.25 of a mile. Then the pilot requests to leave that northeast bearing path and turn 90 degrees and travel towards a southeasterly direction. So there is the 90-degree turn that it takes. Now it's coming down this path. It heads towards the southeast, and that's why I have this path right here between the south and the east directions. The permission is granted. After the airplane goes 1 mile in this direction, in this southeast direction, and that's why there's the mile right there, what bearing should the control tower use to locate the aircraft? In other words, we want to know, what is this? From the actual air control tower to the path that this plane is now on when it finishes. And they want to locate this plane and where it's at after it finishes doing these turns that have been described. Okay, starts off on a northeast bearing of 29 degrees, travels for a quarter of a mile, makes a sharp right turn, travels for a mile in a southeast direction, and then it finishes in a specific location, and the air control tower wants to locate it. So you're really looking for this, but you're going to have to work within the right triangle. Okay, so if we know that this is 29 degrees, and if somehow we could find this theta, which is inside the triangle, we could go 29 plus the theta plus the x is 180. From here, right back to the same line. Here's this north-south line. If you're on that north-south line, if you're standing right on the north-south line, if you have to travel through these three angles, those three angles add up to 180. So if we could find this one, that would be the last one remaining, and we could complete the problem. So I'm going to go after theta first. Okay, so let's see. If I'm standing here and I want to use opposite, because across from the right angle is the hypotenuse. Okay, so if I want to use opposite and adjacent, that means I'm using the 1 and the 0.25. So to find theta, I'm going to go tan of theta is equal to opposite over adjacent. So 1 divided by 0.25 is 4. You can always put it in your calculator if you'd like. That's equal to 4. I really want to find theta, so I'm going to go inverse of 4 is equal to theta. And that's equal to 75 point, I'm going to leave it like this right now since I'm in the middle of the problem, even though the whole thing is still right there in my calculator window. Okay, I'm not there yet because they really want to know what this is right here. So if this is what you're looking for, then you have to realize that this plus this angle plus this angle is 180. Those three added up together add up to 180. So now I'm going to find x. And for that, I'm just going to go 180 minus the 29 minus the angle that I just found. And that'll give me the answer to this question, which is what bearing should the control tower use to locate the aircraft? If I'm going to talk about bearing, I first need to find the angle, but the bearing from the air control tower is that this is on a southeasterly pattern. It's between, or a southeasterly bearing, because it's between the south and the east directions. I just need to know how many degrees from south to east is this path bearing. Okay, so I'm going to find that angle right now. 180 minus the 29 minus the 75.9638, just to be more accurate, and I get 72.0 degrees. This is approximately 72.0 degrees. So final answer is south 72, southeast bearing of 72 degrees. Okay, so that's number 12. Let me check these before I move on to the next problem. Oh, please excuse the dog snoring in the background. He insists on laying here by my feet. Okay, so southeast. Oh, let me just check these real quick. So this is 1 divided by 10. Okay. Okay, yep. Okay, then moving on to number 13. In problem number 13, this says a highway whose primary directions are north-south is being constructed along the coast. Near a city, a bay obstructs the straight path of the road. Since the cost of a bridge is prohibitive, engineers decide to go around the bay. The illustration shows the path they decide on and the measurements taken. What is the length of the highway needed to go around the entire bay? Okay, so let's get a fix on what they're asking us for here. Okay, so only measurements we have is that all the way across this bay here is 7. This is a distance of 1, so those are the things that are given. And then we want to go all the way around, so that means if we want to go around this bay, we're going to need this. I'm just going to call this R1. We're also going to need this distance from here to here. So I'll just call this X. And we're going to need this distance right here because we want to build highway that goes up here, across, and down this way. Okay, so first thing I'm going to do in order to find R1 is I'm going to work inside this right triangle right here pointing to the left. So in that right triangle, I have a right angle. If this is 155 degrees right in here, then from here all the way back to this horizontal line is 180. So 180 minus the 155, that is that exterior angle. That 155 plus the angle adjacent to it is 180. So that would be 5 to get to 70, 15 degrees. Or let's see. Yeah, 180. Yep. So 15 degrees. 5 to get to 70. Nope, 25. Sorry. Supposed to be a 25. Okay, so this is 25 degrees right here. Okay, and if I'm going to find this R1, I have just, taken this right triangle out of the picture so that we can concentrate on that. And if I'm going to find R1, let's see, what could I do here? Now it looks like let me see, on this picture, this is what we have. If we've taken it from this main picture, this distance would be equal to this distance. So we actually do have this. There's a 1 right there. Because again, that vertical leg is the same thing as that. If this is 1, this is 1. We also have that. So we do have some things to work with here. So now we can go, let's see, I want to find the R1, and it's the hypotenuse, so I could use sine here. Sine of 25 degrees would be opposite over hypotenuse. Sine of the angle I'm standing on, and then definition of sine, which is opposite over hypotenuse. So 1 over this R1 that I'm looking for. Sine of 25 would be 0.4226. Okay, and if you're going to solve for R1, it cannot be in the denominator. Switch these two. Let R1 take the place of the 0.4226, and that value will jump down here in the denominator position. And you end up with 2.362. Okay, and we're in miles. Okay, part 2. I'm going to look for R2 now. Okay, so for part 2, I'm going to look for this value now right here because I have to find this piece. I have to find the R2 as well. So now I'll use that other triangle, which also has a leg of 1. It's got a 145 degree angle on the exterior, but that exterior angle combined with its adjacent angle make up 180. So 180 minus the 145 is 35. So that would be this angle right in here. Okay, and then we're going to go looking for R2. So it would be standing on 35, opposite over hypotenuse once again. So sine of 35 is equal to opposite over hypotenuse. Okay, we're going to go get sine of 35. So sine of 35, that'll be 0.5736. 0.5736 is equal to 1 over the length R2. But these two switch places, and you would end up with R2 is equal to 1 over 0.5736. So 1 divided by the answer that's still in the window there would be 1.7434. Okay, so we have this, and then the other thing that we need to figure out is what is the top value. So if we're going to be able to find that top value, here's the thing. The 7 is for the entire distance from here to here. Let me slide down that picture. That's what the 7 stands for. It's the entire distance from there to there. So if we knew the bottom of this triangle and the bottom of this triangle, we could subtract it from the 7 and then we could get x. So that's what we're going to have to do here. So moving into part 3, always the problems at the end are going to be a little bit harder. So once again, we had a triangle that had to do with this 155. There it is right there. That 25 came from subtracting 155 from 180. So we can work on this triangle and find this down here. Doesn't matter what you call it. I'm just going to call it Z, just to give it a name. And I want to find the bottom of this triangle also. The triangle that resulted from the 145 was this 35. I'm going to find this value also, because I need both of those values. So let's keep working on those triangles. Okay, so let's find Z. We already found out that R was equal to, that R1 was equal to 2.3662. Now if I want to find Z, I could actually just go, I really don't need this 2.3662, but I went ahead and put it on there. If I wanted to find Z, I just need to drag Z into the problem. I could go opposite over adjacent, and that would be tan. So I could go tan of 25 degrees using SOHCAHTOA. Tan of 25 is opposite over adjacent. 1 over Z. Okay, and then I can do tan of 25, which is 0.4663. 0.4663. That's equal to 1 over Z. And then I can switch these two just because the unknown is down here in the denominator. So Z would be equal to, just let the 0.4663 come in its place. Pop over into its place. So 1 divided by the answer that's still in my window would be 2.1445. That's what this is, 2.1445. And then down here, that has to do with this triangle. And once again, I could use tangent. I could go standing on this 35-degree angle, and I could go opposite over adjacent. I can go get this in the calculator, which would be 0.7002, which would be equal to 1 over G. I can switch places with these two so that I can solve for G. Nope, that's not going to work. Looking for a pencil that actually works here. Okay, so G would go in the place of the 0.7002, and that number would kind of pop right into that place. And then I would have G is equal to 1 divided by, so that would be 1.4281. 1.4281. Every pencil I'm using is breaking. 1.4281. So that would be this piece down here. Okay, I put those in the diagram now. So I was on my way to trying to find this. However, the 7 stood for the distance from here all the way to here. So I wanted to find just this distance right here. That would be just this, which came out to be 1.4281. And I wanted to find the bottom right here, which was this. Because if I take the entire 7 and I take off this piece and I take off this piece, then I have this piece right in the middle, which is equal to this piece. So in the end, x is equal to 7. Take off the 2.1445 and also take off the 1.4281. So x is equal to 7. Take off the answer that's already there. Take off the 2.1445. You have 3.42735. I don't know what this said to round to. 4274. Okay, so I now have this. And remember, go back to the main question. So this is just kind of like a summary of what you did in each problem, only you're doing it over and over again because it's a multi-part problem. You're asked to build a highway that goes clear around the water. So you had to come up this side. Thus, we had to use this right triangle to find R. I had to do the same thing in this right triangle so I could come down this path and build part of the highway here. What had the most amount of work is finding this, because to find this, you had to use the 7 but take off the bottom of this triangle and the bottom of this triangle from that entire 7 that they gave you. So that meant we had to find one of the legs of this triangle, which turned out to be 2.1445, and we had to find one of the legs of this other triangle. We subtracted both of those quantities from the 7 and finally got this distance. So in the end, to build a highway that goes from here to here, across, and then down, ultimately, that is the final step of the problem. So, total distance is now R1 plus the x to go across plus R2, and that was, let's see, R1 was 2.3, 6, 6, 2. The x was 3.4274, and the R2 value was 1.7434. Okay, so adding all those together, 2.3662 plus 3.4274 plus 1.7434. Checking on my numbers, and I get 7.537. And then I believe, let's see, they asked you to round to 2 decimal places. So just 7.54. Okay. All right, so heavy on the steps. Last problem. Okay, so last problem concerns a blimp. You do have a triangle in this picture. You can't see it very good, but those are the sides right there. This is the bottom. It has a height of 400. This is another line right here. So you got some parallel lines right here. And I am going to move over to a diagram that I drew that's a little bit clearer. We're trying to find the distance from the sports stadium to the planetarium. So I just drew this a little bit bigger for you. Okay, so we have 46 and we have 26, and we're going to bring those down into the triangle. Again, this has to do with given parallel lines. You have the ground and this horizontal line up here. Those are the parallel lines. These are the transversals, so alternate interior angles are equal. That allows you to bring this 40 down into the triangle. They are on alternate sides of the interior of parallel lines, and therefore they're equal. Likewise with this angle and this angle. Okay, so if you're going to try and find the total distance from here to here, you have to work with the bottoms of each of these triangles, just like we did in the previous problem, only this problem has much less steps. All we need is this and this. I'll call this x sub 1, I'll call this x sub 2, and I'll just call this plane x. Okay, so if I'm going to find x sub 1, I'd be standing on this 40-degree angle and using opposite over adjacent. That's tan. So tan of 40 degrees is equal to opposite over adjacent. Okay, we're going to get in our calculator and do tan of 40, which is 0.8391. Okay, so we're there. Variable that we're solving for is down in the denominator, so we're going to switch these two to get this up to numerator level. This is going to be 400 divided by, still in my window, and that'll be 476. 70 feet. And then we'll do the same thing with this other triangle. I did this one where I went tan of 40 is equal to 400 over x sub 1. Likewise, I'll stand here on the 26-degree angle and do opposite over adjacent again. So tan of 26 is equal to opposite over adjacent. We're going to get the tan of 26, 4877. So 4877, that's equal to 400 over x sub 2. We need to switch these two, getting the x2 up there at numerator level, and the 0.4877 takes its place. So x2, 400 divided by the answer that's still there, 820.12. And then if you want the total distance from here to here, from the sports stadium to the planetarium, just add up this distance, x1 plus x2. Okay, so this was part 1, part 2, part 3. So total distance is equal to x1 plus x2. That could be 1296.82. Okay, and I believe that that concludes. Let's make sure. And that's it. So that concludes section 8.1.